The Quilted Multiverse. Not aliens, not other dimensions, just more space. Here's the pitch. If space is infinite, genuinely, truly infinite, not just very large, then it doesn't just contain more stars past what we can see. It contains more of everything. Repeats, copies. Given enough space, every possible arrangement of particles has to happen more than once, somewhere, eventually. The math behind this one isn't exotic, it's combinatorics. There are only so many ways to arrange a finite number of particles in a finite volume, a staggering number, but finite. Roughly 10 to the power of 122 possible quantum states in a region the size of our observable universe. Big, but not infinite. Now stretch space out past that region forever in every direction, and the arrangements have to start repeating. Not because the universe is trying to, because there are only so many ways to shuffle a deck of finite cards, and if space never ends, you deal that deck an infinite number of times. Here's the fact that changes everything. Calculations based on this reasoning put your nearest identical copy, same face, same house, same argument you had this morning, at roughly 10 to the power of 29 meters away. Not light years, meters. A number so large that writing it in full would require more digits than there are atoms in the observable universe. Let that sink in. Somewhere out there, past any horizon we could ever cross, there might be another version of you reading these exact words at this exact moment for reasons neither of you will ever know. This is the least controversial multiverse on the list. It doesn't require new physics, new dimensions, or new laws. It only requires one thing, that space keeps going past the edge of what light has had time to reach us from. Most cosmologists studying the shape of the universe think that's actually likely. The observable universe is a bubble 93 billion light years wide. Nothing says space stops there. It's just where our particular horizon ends. But here's the catch that keeps this one grounded in real science instead of fantasy. We can never see these other regions. Not with a better telescope. Not in a million years. Light from beyond our cosmic horizon will never reach us because the universe itself is expanding faster than that light can close the gap. This multiverse isn't hidden by mystery. It's hidden by geometry. An infinite quilt of universes stitched from the exact same laws of physics as ours, forever separated by nothing more exotic than distance. So, if the first multiverse is just old-fashioned infinite space, what happens when you ask how that space got here in the first place? Eternal inflation. This is where things start getting stranger and where the theory starts standing on genuinely solid physics. Here's the reframe. The Big Bang wasn't the beginning of everything. According to inflation theory, a well-supported model that explains why the universe looks so uniform and flat, the universe underwent a period of unimaginably fast expansion in its first fraction of a second, ballooning by a factor of at least 10 to the 26 in less than a trillionth of a trillionth of a trillionth of a second. The mechanism behind that expansion is a field physicists call the inflaton. Picture it like a ball perched on a bumpy hillside. Where the ball rolls downhill smoothly, inflation ends, and a universe like ours pops into existence, cooling into stars and galaxies. But quantum mechanics guarantees the field doesn't behave everywhere the same. In some pockets, instead of rolling down, the field randomly fluctuates upward, restarting inflation locally, even while it ends elsewhere. Here's the twist that gives this theory its name. If inflation ends in our patch, but keeps going somewhere else, then inflation never actually stops everywhere at once. It just keeps spinning off new bubbles, forever each bubble becoming its own separate universe with its own Big Bang, expanding away from every other bubble faster than light could ever connect them. The number of bubbles this predicts isn't small. It isn't even large in any normal sense. Under eternal inflation, bubble universes form endlessly, an ongoing process with no final count, spawning new pocket universes at every moment across an ever-growing, inflating background. Here's the fact that should genuinely unsettle you. Some versions of this model predict that the physical constants inside each bubble, the strength of gravity, the mass of the electron, Even the number of spatial dimensions could be different from bubble to bubble, set randomly as inflation ends in each patch. Our universe might just be one roll of an enormous cosmic dice, sitting in a bubble where the numbers happen to land in a way that allows atoms, stars, and stick figures with glasses to exist. Unlike the Quilted Multiverse, this idea isn't just a consequence of infinite space. It's built directly into one of cosmology's most successful models. Inflation is supported by precise measurements of the cosmic microwave background, the leftover glow from 380,000 years after the Big Bang. The theory that explains our universe's uniformity is the same theory that predicts we're not the only bubble. That's either deeply reassuring or deeply disturbing, depending on how you look at it. But testability here gets shaky fast. Bubble universes, if they exist, lie beyond an inflating region expanding faster than light, permanently unreachable, permanently unobservable in principle as well as in practice. Physicists have looked for one narrow exception: a collision scar. If another bubble ever brushed against ours before inflation pushed us apart, it might leave a faint bruise in the cosmic microwave background. Several research teams have searched for exactly that signature. So far, nothing conclusive. Eternal inflation remains one of the most seriously considered ideas in cosmology, and one of the hardest to ever put to a direct test. So space might be tiling itself into countless separate bubbles. But what if the multiplying doesn't happen out there in space at all? What if it happens every time you make a choice? Many worlds. This is the multiverse born not from cosmology, but from the strangest, best tested theory in all of physics: quantum mechanics. Here's the reframe. In the standard telling of quantum mechanics, a particle exists in a haze of possibilities, a superposition, until it's measured, at which point the haze collapses into one single definite outcome. Nobody has ever fully explained how or why that collapse happens. It's simply bolted onto the math as a rule. The many worlds interpretation proposed by physicist Hugh Everett in 1957 takes a different approach. It says there is no collapse. Every possible outcome of every quantum event actually happens, just each one in its own separate, non communicating branch of reality. The universe doesn't choose an outcome, it splits cleanly into a version where each outcome is real. Here's what makes this different from every other candidate on this list: it doesn't add anything to physics. Many worlds uses exactly the same equation, the Schrödinger equation, as every other interpretation of quantum mechanics. It doesn't predict new particles or new forces. It just refuses to add the extra unexplained rule that says the wave function collapses. Remove the patch, and the math implies branching universes as a direct, unavoidable consequence. The scale of that branching is difficult to hold in your head. Every radioactive decay, every photon hitting a detector, every quantum event anywhere in the universe, at every moment, potentially splits reality again. Under this interpretation, an almost incomprehensible number of parallel timelines could be branching into existence continuously, each one just as real and just as populated as this one, each one convinced it's the only one. Here's the fact that changes everything. Many worlds isn't a fringe idea whispered about at the edges of physics. In surveys of working physicists and philosophers of physics, it consistently ranks among the most popular interpretations of quantum mechanics, sometimes the single most popular, ahead of the textbook Copenhagen interpretation most students are taught first. Serious, credentialed scientists, not science fiction writers, take this seriously as a literal description of reality. But here's the problem that keeps it firmly in the interpretation category rather than confirmed science: every branch is, by construction, permanently cut off from every other. There is no experiment, even in principle, that lets you detect another branch, communicate with another branch, or verify that branching happened at all instead of ordinary collapse. Two competing descriptions of reality, making identical predictions for every experiment ever run, differing only in a philosophical claim about what's really happening behind the math. Untestable doesn't mean unpopular. It just means physicists are choosing sides based on elegance, not evidence. So parallel realities might be splitting apart in every atom right now, with no fingerprint left behind. But what if the multiverse isn't made of universes splitting from ours at all? What if it's made of every mathematical structure that could possibly exist? The mathematical universe hypothesis. This is where physics starts blurring into something closer to metaphysics. Here's the reframe, and it's the strangest one so far. Physicist Max Tegmark proposed that our universe isn't merely described by mathematics. It literally is a mathematical structure, nothing more, nothing less. Not a physical thing that happens to obey equations. The equations themselves existing are the universe. Push that idea one step further, and you get the multiverse version. If our universe is just one mathematical structure among the equations that could exist, then every self-consistent mathematical structure, every one that doesn't contradict itself, exists in exactly the same sense ours does. Not as an abstraction, as an actual experienced reality from the inside by whatever inhabits it. Here's why some physicists find this compelling instead of absurd. Physics has spent 4 centuries getting spookily good at predicting reality using pure mathematics, equations written on paper, decades before anyone built the equipment to test them, turning out to match experiments to 9 or 10 decimal places. Tegmark's argument flips the usual question. Instead of asking why math describes the universe so well, it asks whether the distinction between the math and the universe was ever real to begin with. Here's the fact that should genuinely unsettle you. Under this hypothesis, there's no privileged universe. Every consistent equation is a world populated by observers who experience their own mathematics as solid, physical, inescapable reality, exactly the way you're experiencing this sentence right now. Somewhere in the landscape of all possible mathematics, there might be a version of physics with 4 space dimensions instead of 3, or with no time at all, fully real to whatever lives inside it. This is, by most physicists' own admission, one of the most speculative ideas taken seriously in modern cosmology. It makes essentially no testable predictions that distinguish it from ordinary physics. It's closer to a philosophical stance about the nature of existence than a scientific theory you could falsify in a lab. Interesting. Maybe even true. But currently unfalsifiable in any practical sense. A boundary marker for how far multiverse can stretch before it stops being physics and starts being philosophy. So, if reality might be built from every equation that doesn't contradict itself, what happens when you ask the same questions inside the leading candidate for a theory of everything? The string theory landscape, back to something with actual mathematical teeth tied to real ongoing research in fundamental physics. Here's the reframe. String theory proposes that every particle in the universe is actually a tiny vibrating string, and different vibration patterns produce different particles. Electrons, quarks, photons, all just different notes on the same instrument. To make the math consistent, string theory requires extra spatial dimensions beyond the 3 we experience, typically 6 or 7 more, curled up impossibly small. Here's where the multiverse creeps in. Those extra dimensions can be curled up, physicists call it compactified, in enormous numbers of different geometric shapes. Each distinct shape changes the physical constants of whatever universe unfolds from it. Different particle masses, different force strengths, different fundamental rules. Estimates for the number of possible shapes run to roughly 10 to the 500. Not infinite, but large enough that really infinite barely feels like an exaggeration. That staggering number of possibilities has a name, the string theory landscape. Each of those 10 to the 500 configurations is a candidate for its own separate universe with its own separate laws. And under certain versions of eternal inflation, each one could actually be realized somewhere in some inflating bubble as an actual physical universe rather than just a mathematical possibility on a chalkboard. Here's the fact that changes everything about how physicists talk about their own field. Faced with 10 to the 500 possible universes, some physicists have started using the landscape to explain something that used to look like a miracle. Why the constants of our universe are so precisely tuned for stars, chemistry, and life to exist at all. If nearly every possible universe is sterile and dead, but a vast landscape of them exists, then of course we find ourselves in one of the rare ones that works. Nobody observes a universe incompatible with observers. That argument, called the anthropic principle, is deeply controversial inside physics itself. Critics call it a retreat from real explanation, using an unfalsifiable multiverse to excuse away a fine-tuning puzzle that a better theory might actually solve. Supporters call it the only rigorous answer available once you accept the landscape is real. Both camps are working physicists, not cranks, and the argument hasn't been settled. String theory itself remains without a single direct experimental confirmation decades after being proposed. No detected strings, no detected extra dimensions, no confirmed supersymmetric partner particles, the kind string theory strongly favors, despite years of searching at the Large Hadron Collider. The landscape built on top of an already unconfirmed theory is speculation stacked on speculation, mathematically rich, but resting on a foundation that hasn't yet been nailed down. So the landscape might be vast beyond counting. But what if entire universes aren't just mathematical possibilities sitting on a landscape? What if they're physical objects drifting through some larger space, occasionally colliding? The Brane and Cyclic Multiverse. This is where the geometry gets almost tactile. Here's the reframe. In certain versions of string theory, our entire universe, all three dimensions of space we experience, everything in it, might be a membrane, or brane for short, floating within a higher dimensional space called the bulk. Picture two enormous sheets of paper, each one a complete universe, both floating separately within some larger, unseen volume. The cyclic model built on this idea proposes something genuinely wild. These branes drift toward each other across the bulk, collide, and the energy of that collision is what we experience from the inside as our own Big Bang. Not a single unique origin of everything. A repeating event, a cosmic collision happening over and over on a time scale of roughly 1 trillion years per cycle. Here's the fact that changes everything about how you'd picture the beginning of the universe. Under this model, the Big Bang wasn't a singular moment when everything sprang from nothing. It was a collision between two pre-existing universes that had already been around, potentially, for a previous 1 trillion-year cycle of their own, and the one before that, and the one before that, stretching backward without any true starting point at all. This idea does make at least one prediction that real instruments could, in principle, check the pattern of gravitational waves left behind from the Big Bang. Standard inflation and the colliding brane model predict different signatures in that primordial gravitational wave background. Detecting or ruling out one specific pattern, a particular kind of polarization swirl in the cosmic microwave background called B modes, could genuinely distinguish between them. Experiments have been hunting for that swirl for over a decade. So far, none of the confirmed detections have matched what the brane model needs. That makes this one of the more testable entries on this list, at least in principle, a real falsifiable fingerprint sitting in data we're already collecting. It just hasn't shown up yet. Whether that means the brains aren't colliding or the signal is simply too faint for current instruments remains an open question actively being worked on. So, universes drifting and colliding somewhere in a higher dimensional bulk. But what if you don't need brains or extra dimensions at all? What if every black hole in the sky is already quietly building a universe of its own? Black holes spawning baby universes. Of all the multiverse candidates on this list, this one comes from staring at an object we've actually photographed. Here's the reframe. Inside a black hole, according to general relativity, gravity crushes matter down toward a singularity, a point of theoretically infinite density where the equations of physics stop making sense. Some theoretical physicists, including Lee Smolin, have proposed that this collapse doesn't actually reach true infinity. Instead, at extreme densities, quantum gravity effects take over, and the collapsing matter rebounds, not explosively outward into our universe, but into a newly formed, causally disconnected universe of its own, expanding on the other side of the singularity. Here's what that would mean if it's true. Every single black hole in existence, and current estimates suggest there are around 40 octillion of them, scattered across the observable universe alone, could be the seed of an entirely separate universe, budding off through its own private Big Bang, forever inaccessible from ours. Smolin took the idea one step further with a genuinely bold proposal called cosmological natural selection. If baby universes inherit slightly mutated versions of their parent universe's physical constants, then universes that happen to produce more black holes would produce more offspring universes, generation after generation. Run that process long enough, and you'd expect the multiverse to be dominated eventually by universes finely tuned to be extremely good at making black holes. Here's the fact that makes this proposal stand out from most of the others on this list. It's actually falsifiable, at least in principle. If this hypothesis were true, our universe's physical constants should sit near a local maximum for black hole production, tweak any one of them slightly in either direction, and you should get noticeably fewer black holes, not more. Physicists have actually run these calculations. The results are debated, not settled, but the proposal makes a concrete prediction you could, in theory, check against real physics, a rare trait among ideas on this list. It remains a minority position, and most physicists working on quantum gravity are skeptical. But it's a reminder that untestable isn't a fixed property of every multiverse idea. Some at least gesture toward evidence. This one just hasn't convinced most of the field yet. So maybe universes are budding from black holes generation after generation, quietly selecting for their own reproduction. But what if the deepest question isn't how many universes exist at all? What if it's whether any of them, including this one, is even the base layer of reality? The simulation argument, not technically a multiverse theory, but it belongs on this list because it changes what universe even means. Here's the reframe. Philosopher Nick Bostrom formalized this argument in 2003, and it isn't a claim that we are definitely living in a simulation. It's a logical trilemma, 3 options, and Bostrom argues at least one has to be true. Either civilizations almost always go extinct before developing the technology to run realistic ancestor simulations, or civilizations that reach that technology choose almost universally not to run them, or we are almost certainly living inside one right now. Here's why the third option gets so much attention. If even one advanced civilization anywhere ever runs even a modest number of simulated universes full of conscious beings, the simulated minds would vastly outnumber the original base reality minds. Simple statistics. If simulated observers vastly outnumber reals ones, and you're an observer with no way to check which category you're in, the odds say you're more likely to be one of the many rather than one of the few. Here's the fact that changes everything about how this connects to actual physics, not just philosophy. Some theoretical physicists have pointed out that if reality is computed, there might be detectable artifacts, a kind of underlying resolution limit or lattice structure, similar to pixelation in a rendered image, potentially showing up as tiny irregularities in how cosmic rays propagate at extremely high energies. A few papers have proposed specific checkable signatures. None have been found. Most physicists consider this a long shot, not a real lead. This idea is arguably the most philosophically loaded entry on the entire list and the least grounded in established physics. It isn't derived from any confirmed theory the way eternal inflation is derived from cosmic inflation, or the way the string landscape is derived from string theory. It's a probability argument built on assumptions about technology, civilizations, and consciousness that nobody can currently verify. Compelling as pure logic, nearly untestable as science. So here's where that leaves the entire list. 8 ways the universe might not be the only one, ranked from grounded to nearly ungrounded, and it's worth being honest about exactly how shaky the ground gets. The Quilted Multiverse needs almost nothing extra, just space that keeps going, using physics nobody seriously disputes, even though the other regions are permanently unreachable by light. Eternal inflation is built directly into a well-supported cosmological model, and it makes at least one narrow, searchable prediction. A bruise in the cosmic microwave background from a bubble collision hunted for but not yet found. Many Worlds uses the exact same equations as ordinary quantum mechanics, changes zero predictions, and is popular among physicists, yet offers no experiment, even in principle, to confirm the other branches exist. The mathematical universe hypothesis and the string theory landscape both rest on real serious mathematics, but drift further from anything a lab could check. One is closer to philosophy, the other inherits the unconfirmed status of string theory itself. The cyclic Brane multiverse actually makes a falsifiable prediction we're still testing today in real gravitational wave data. Black holes spawning baby universes offers a genuinely checkable idea about our own physical constants, even if most physicists remain unconvinced. And the simulation argument sits at the far edge, a logical trilemma dressed in physics language, with almost nothing a telescope or a detector could currently confirm or deny. Let that sink in. Not one of these 8 ideas has been directly confirmed. Not one has been definitively ruled out either. Somewhere between this is basically just geometry and this is basically philosophy. An entire field of serious credentialed physicists spends careers working the middle ground because the alternative, assuming our universe is the only one, the only roll of the dice, might be the least likely option of all. Not bad for stick figures on a rock.